In this lecture, let us look at the band pass filter and band stop filter of infinite impulse response type. Okay, so we are looking for the simplest band pass filter. Now, as we saw in the finite impulse response case, the minimum order that was needed was 2. Okay, in fact, you cannot make a first order band pass filter. One cannot make a first order band pass filter or band stop filter. So we need minimum order 2. The minimum order that you need is 2 to make a band pass filter or a band stop filter. And in the case of IIR, infinite impulse response filter, the band pass filter and band stop filter are constructed based on trial and error method. Okay, so the transfer function is obtained, or the transfer function has been worked out by trial and error method. So let me write down the transfer function. So the simplest second order band pass filter is h of z is equal to, in the denominator we have 1 minus beta times 1 plus alpha z to the minus 1 plus alpha z to the minus 2. Okay, so this denominator polynomial is obtained by trial and error method. And if you take if you remember your FIR case, the numerator was 1 minus z to the minus 2. Okay, so therefore the numerator is the same as that of FIR. So there is no change in the numerator. Numerator as that of FIR case. In FIR we had a 1 minus z to the minus 2. And to make sure that the maximum value is unity. Okay, maximum value means what? We are constructing a band pass filter. So band pass filter will be like this, and we need to make sure that the maximum value should be unity. So that I need some multiplying constant. Some multiplying constant here. What should I put? So the multiplying constant is 1 minus alpha by 2. So therefore your h of z is modified as 1 minus z to the minus 2 in the numerator. In the denominator 1 minus beta plus 1 times 1 plus alpha z inverse plus alpha z to the minus 2, and you multiply by 1 minus alpha by 2. Why did I need this multiplying constant? Because to make sure that the maximum value is 1. Okay, so this 1 minus alpha by 2 ensures that the maximum value is unity. Now you can see that at z equal to plus or minus 1, the magnitude would be 0. You substitute z equal to plus 1 and this, the magnitude would be 0. You can substitute here. So h of 1 is equal to 1 minus 1 squared. Doesn't matter what is going to happen in the denominator. You can substitute 1 minus beta times 1 plus alpha times 1 plus alpha. That's it. So numerator is 0 and the denominator is non-zero. Therefore it is 0. Similarly, h of minus 1 also will be equal to 0. Right, so the numerator is 0 for z equal to plus 1 and the numerator is 0 for z equal to minus 1. Z equal to plus 1 means what? This z equal to plus 1 corresponds to omega equal to 0. Similarly, z equal to minus 1 corresponds to omega is equal to pi. So what is our range of vision in digital filter? 0 to pi. Therefore my minimum frequency is 0 and the maximum frequency is pi. The minimum frequency, the value is 0 and the maximum frequency the value is 0. In between my function goes like this and comes back. Maybe at this point it reaches the maximum value, and that maximum value is going to be 1. Therefore, the first condition for band pass filter is met. Second thing you have to do is to find where does the maximum occur. Okay, at which point, this point we need to know at which point the maximum occurs. Now it is a bit of algebra, okay, you can carry out and you can easily show that the maximum occurs at, let me call this frequency is omega is equal to omega naught, and this point is omega is equal to pi, omega is equal to pi this point, and this point omega is equal to 0. Let me call this point omega naught. Omega is equal to omega naught. Now this, how can you find out this omega naught? Omega naught is equal to cosine inverse of beta. This you can easily show it, okay, it's a little bit of algebra. Therefore cos of omega naught, this omega naught is a frequency at which the maximum occurs. Okay, so this is beta. So this is a formula, through that you can find out. So what do you understand from this? Cos omega naught equal to beta. What can we infer from this? By choosing the value of beta, one can shift the center frequency or maximum frequency or resonant frequency. Okay, so you can shift. So based on the value of beta, this omega naught can be changed. Either you can have like this, or you can have like, you can have like this, or you can have like this. You can change the center frequency. So the center frequency depends on the value of beta. The parameter is beta controls the center frequency. But in the FIR case, you can't control. Okay, it is a fixed one. What is the value of that center frequency? Pi by 2 in FIR case. So you have a filter like this, and this is pi 0. My center frequency somewhere here, omega naught. Okay, the characteristic would be something like this. And as I said, the maximum value is 1, and the center point is omega naught. And you can find out the cutoff frequency, like 1 by root 2 times of the maximum value, that is, this is 0.707. Okay, or you can say 1 by root 2. This is my h of e to the j omega magnitude. Now you get h of e to the j omega magnitude to 1 over root 2 and solve that. Okay, and it cuts this point and this point. Let me call this frequency omega 1 and this frequency omega 2. Okay, so then and first we can show that cos omega naught is equal to beta. Cos of omega naught is equal to beta, that is the center frequency, and at omega naught the maximum occurs, and the maximum value is how much? 1. Why this maximum value is 1? Because we modified the transfer function by the scalar. Where is the scalar? This is the scalar. And you can also show that the magnitude down 3 dB at frequencies omega 1 and omega 2, such that omega 2 minus omega 1 is equal to cosine inverse of 2 alpha divided by 1 plus alpha square. Okay, and what is this omega 2 minus omega 1? This is defined as bandwidth. Okay, so we saw that the same holds for a low pass filter as well as high pass filter, bandwidth. In low pass filter, omega c is the cutoff frequency and also bandwidth. Okay, omega c is the bandwidth of the low pass filter. So for low pass filter, omega c is equal to cosine inverse of 2 alpha divided by 1 plus alpha square. If you recall, the low pass filter would be like this. You take this point and this is omega c, and this is called the bandwidth of the low pass filter, 0 to omega c. And this bandwidth is given by this expression, and here this bandwidth also given by the this bandwidth also given by the same expression. Whether it is a band pass filter or a low pass filter or high pass filter, the bandwidth is given by the same formula. But here in the low pass filter it is going to be omega c. In the band pass filter it is going to be omega 2 minus omega 1. For the high pass filter, what is the bandwidth? In case if we have the high pass filter like this is pi, you take 3 dB and this is your omega c. Now this is my bandwidth. How can I find this bandwidth? Pi minus omega c. Okay, therefore pi minus omega c is equal to cosine inverse of 2 alpha divided by 1 plus alpha square for high pass filter. So high pass filter, the bandwidth is obtained using this formula. Okay, and this point corresponds to 1 over root 2 of the maximum amplitude. The maximum amplitude is 1, and this frequency is the cutoff frequency for the high pass filter, and this is the bandwidth, and this is omega. So the bandwidth is going to be pi minus omega c. That pi minus omega c again given by cosine inverse of 2 alpha divided by 1 plus alpha square. So whether it is high pass filter or low pass filter or band pass filter, for the case of band pass filter, this is a formula. For the case of low pass filter, this is the formula. Low pass filter, this is how you calculate the bandwidth, and for high pass filter, this is how you calculate the bandwidth. Okay, and once again, if you want to find out alpha for a given bandwidth, then you have to solve the quadratic equation. Okay, so bandwidth is equal to cosine inverse of 2 alpha divided by 1 plus alpha square. Okay, so cosine of bandwidth is equal to 2 alpha divided by 1 plus alpha square. So if you cross multiply this and bring it to the left hand side, then it becomes a quadratic equation, and you solve the quadratic equation in order to find out the alpha. Notice two interesting things can happen here, namely the first one is the two constants alpha and beta are independently determined. That is the beauty of this transfer function. Independently determined. Okay, one parameter of the band pass filter. And the second point is beta determines what? The center frequency. It has no effect on the beta, has no effect on the bandwidth. And third point is alpha determines the bandwidth. So for the same center frequency omega naught, you can get various bandwidth, okay, by simply varying alpha. Like let's say this is my omega naught. What is this? This is the bandwidth, omega 1, omega 2. Now for the same frequency you can have like this. Now this is my new omega 1 and this is my new omega 2. Now look at here, this omega naught is changed, but the bandwidth is changed. This is bandwidth 1, let's say, and this one is bandwidth 2. So by varying alpha, one can change the bandwidth without changing the center frequency, right? So that is the beauty of this design, this digital filter. So if you don't want to change the center frequency, but you would like to change the bandwidth of the filter, or you want to make a narrow bandwidth filter, sometimes you need a narrow band pass filter. Narrow band pass filters, especially in communication, we need a narrow band pass filter. So in that case, one can make very narrow bandwidth. How will you do it? Let me draw it here. You can make like this, like this. Now look at, this is my new bandwidth. So this is the narrow band. Okay, so this between this point, but again notice here the center frequency is not changed. Center frequency is the same as the previous case. So one can change the bandwidth of the filter without changing the center frequency, or you can change the center frequency without changing the bandwidth. That also possible. The entire curve is shifted to the left or to the right. That also possible in this design. Okay, so h of z equal to the denominator 1 minus beta times 1 plus alpha z to the minus 2 plus alpha z to the minus 2. Sorry, this is z inverse, and the numerator 1 minus z to the minus 2, and here there is a multiplying factor 1 minus alpha by 2. And this, if you draw the realization diagram of this transfer function, so how will you draw the realization diagram? By using delay, multiplier, and then summer. That's all. Okay, so addition, multiplication and delay, these are the operations that one will do in the digital signal processing. So in this, once you do the realization of this transfer function, then 1 minus alpha by 2 is simply what? A multiplier. So that if you change the value of the multiplier, you change the bandwidth and can get the desired bandwidth. You simply change the value of the multiplier in your design, in your program, in your digital signal realization diagram, either in the hardware or in the software. You simply change the value of the multiplier. Simply you can change the bandwidth of the digital filter, but this is not possible in the analog filter design or analog signal processing, because the bandwidth again in turn depends on the value of resistance, inductance, capacitance, and again changing the value of resistance, inductance and capacitance. It is not that much easy, but in digital signal processing you can easily change the multiplying value. Simply you can change the value of the multiplier 1 to 2, 1, 3, 4 like that, and then you dump the program on the DSP chip and the bandwidth will be changed. Similarly, if you vary the beta value in the realization, then your center frequency also changed. So that is the advantage or usefulness or easiness of your digital signal processing. So very easily you can change the bandwidth and very easily you can change the center frequency. Okay, so if you change the value of multiplier, you change the bandwidth and can get the desired bandwidth. This is an extremely important feature of any filter, that the parameters should be controllable independently of each other. Okay, now what is omega naught divided by bandwidth? Do you remember this formula? This is called a Q factor. Okay, Q of the filter. Okay, quality factor of the filter. So the Q of the filter can be changed independently of the center frequency. If alpha is kept constant and simply beta is changed, because beta controls center frequency and alpha controls bandwidth. Therefore Q is equal to function of beta, because beta controls the center frequency, and function of alpha. Okay, now you keep alpha constant and then change beta, then you can get a series of what are called constant Q filters. That is, all filters have the same Q but different center frequency. So this transfer function has been worked out by, as I said, trial and error method by the engineers, by the research community. And this transfer function is a versatile transfer function. It has two parameters, one is alpha and one is beta, which can independently control the center frequency and the bandwidth, or equivalently the Q value. Now where are the zeros of this transfer function? The zeros are at plus or minus 1. Okay, a 0 at plus 1 is needed for making the DC response equal to 0, and a 0 at minus 1 is needed to make the response at omega is equal to pi equal to 0, and this at omega is equal to 0 to 0. Okay, when you substitute plus 1, the response would be 0 at omega is equal to 0. When you substitute z equal to minus 1, that corresponds to pi, and this point again the response is 0. So in between the curve goes like this. At this point omega is equal to 0 means DC response. Omega is z equal to minus 1 means it is pi in the frequency axis. So these 2 points are ensured that they are at a 0 level. Now where are the poles? 0 is fine, okay. Easily you can find out from the numerator polynomial by equating the numerator polynomial to 0. So z equal to plus or minus 1. Now where are the poles? Okay, well, you can work it out from here and you can find out. Now do you think the poles are real or poles are complex? Okay, take this denominator polynomial 1 minus beta times 1 plus alpha z to the minus 1 plus alpha z to the minus 2. Solve this equation. Okay, now the question is, poles, are they real or are they complex? Or are poles complex? That is a question. If you solve it, they will be complex. With the real poles you can achieve very little, okay, but the Q is very restricted. But the moment if you make it complex poles, then you will get a high value of Q. Okay, so generally the poles are complex. If you make real poles, then there will be lot of restrictions. Now let me take an example and then we will design a band pass filter. Okay, suppose we want the center frequency is equal to pi by 2, and let's say the bandwidth of the filter is pi by 4. Let's say, so design a IIR band pass filter. Okay, so we want to design a band pass filter whose center frequency is pi by 2 and its bandwidth is pi by 4. So what is the Q value in this case? Q value is center frequency divided by bandwidth. Center frequency is pi by 2 and the bandwidth is pi by 4. So the Q value is 2. Now what is the beta? Beta is cosine inverse of the center frequency omega naught. What is the center frequency? Pi by 2. Cosine inverse of pi by 2. What is the cosine inverse of pi by 2? 0. So beta is 0. One parameter is 0 here. Okay. So beta would be equal to cos omega naught, cos of omega naught, and therefore beta is 0. Now what is the bandwidth? Cos of bandwidth is equal to, if you remember the formula, 2 alpha divided by 1 plus alpha squared. And bandwidth is pi by 4. Cos of pi by 4 is equal to 2 alpha divided by 1 plus alpha squared. Okay, cos of pi by 4 is 1 by root 2, which is 2 alpha divided by 1 plus alpha square. This is a quadratic equation. Again, you solve this, then the roots will be root 2 plus or minus 1. So I have two roots. Either I can take root 2 plus 1, or I can take root 2 minus 1. Okay, now let me take root 2 minus 1. There is no reason that I can take root 2 plus 1. If I take root 2 plus 1, maybe my poles will lie outside the unit circle. So therefore my system will, my filter will be unstable. So let me consider root 2 minus 1. Okay, and whether we will see that poles exist inside the unit circle, because the pole must lie within the unit circle in order to make a stable filter. Okay, so let us choose alpha is equal to root 2 minus 1. Now alpha is a parameter. Okay, it is a multiplier. Okay, there is no concept of attenuating or something, amplifying in digital signal processing. It's a parameter, it's a multiplier, it's a scalar actually. So alpha can be chosen to be root 2 plus 1 also. Let us take root 2 minus 1. Okay, you have to look at the poles. If the poles go out of the unit circle, then you are in trouble. So make sure that the poles should lie inside. Okay, so if you take root 2 plus 1, the poles may lie outside the unit circle. Let us verify that, no problem. Now h of z is equal to 1 minus z to the minus 2, 1 minus beta times 1 plus alpha z inverse plus alpha z to the minus 2, 1 minus alpha by 2. Okay, take the denominator polynomial. So 1 minus beta 1 plus alpha z to the minus 2 plus alpha z to the minus 2, z inverse plus alpha times z to the minus 2. Now this is a quadratic equation in z inverse. Make this let us equal to 0. Now make this quadratic equation in terms of z. Multiply both sides by z squared. So z square minus beta times 1 plus alpha times z plus alpha is equal to 1, 0. Now this equation is in the form of ax square plus bx plus c is equal to 0. What are the roots? X is equal to minus b plus or minus square root of b square minus 4ac divided by 2a. And in this expression, a is equal to 1, b is equal to minus beta times 1 plus alpha, and c is equal to alpha. Therefore, the roots are minus b, minus times minus plus b, b times 1 plus alpha plus or minus square root of b square, that is beta square times 1 plus alpha the square what did I do? Yeah, correct. Minus 4ac, 4 times alpha divided by 2a. 2 times a is 1. Okay, therefore this is beta times 1 plus alpha by 2 plus or minus square root of beta times 1 plus alpha square beta square if you bring this 2 inside the square root, then it becomes 4, and minus 4 alpha divided by 4, and 4 will get cancelled. So I can write beta times 1 plus alpha by 2 plus or minus square root of beta times 1 plus alpha divided by 2 the whole squared minus alpha. So this is the root of the denominator. So these are the two poles. okay, poles of h of z. I have two poles, okay. One pole is, if you take plus you will get one pole, if you take minus you will get another pole. Now this quantity will be imaginary, okay. So the poles in general will be complex because beta is 0 here, so it's an imaginary quantity. Because beta also 0 and you'll get minus, and because of this minus sign the poles will be imaginary. Now let us take alpha is equal to root 2 minus 1, substitute in this one, and beta is equal to 0, okay, and then we will find out the transfer function. So in this case z equal to 0 plus or minus square root of 0 minus alpha. What is alpha value? Root 2 minus 1, okay. So this is plus or minus square root of 1 minus root 2. Is that right? And again I can replace this. Hold on. See, in this formula I substituted, okay. So this is the poles of the system, okay. In this I substituted root 2 is equal to root 2 alpha is equal to root 2 minus 1 and beta is equal to 0. So the first term will disappear and this term also will appear, and you are left with square root of minus alpha plus or minus square root of minus alpha. Let me work it out properly, it is slightly messy now. So z equal to plus or minus square root of minus alpha. I can write plus or minus j times square root of alpha, isn't it? Therefore what is alpha? Alpha is root 2 minus 1. Therefore z is equal to plus or minus j times square root of, again within the square root, root 2 minus 1. So these are the poles of my transfer function. Therefore h of z is equal to, and where are these poles? These poles are located at maybe this point is root 2 minus 1, square root of root 2 minus 1, and this point, it's a circle, unit radius circle. Okay, and this point is square root of root 2 minus 1, and this point is minus square root of root 2 minus 1, okay. These are the, I am sorry, I should not put this symbol. I should put a cross symbol to indicate the poles. And in the numerator, if you look at, what is the numerator? 1 minus z to the minus 2 and equal to 0. 1 minus z to the minus 2 equal to 0. Therefore z equal to plus or minus 1. These are the location of zeros. Therefore 1 0 is at this point, z is equal to 1, and 1 0 is at this point, z is equal to minus 1. Okay. In case if you would have taken alpha is equal to root 2 plus 1, then the poles might have gone outside the unit circle, okay. So and you will be getting unstable band pass filter. Therefore you must be able to justify that, okay. So the poles must lie within the unit circle in order to make a stable filter, okay. So that's it. Now let's talk about a band stop filter. Okay, BSF. BSF. The band pass filter and the band stop filter, they do not obey the correspondence that the low pass and the high pass obey. If you recall, low pass filter to high pass filter is obtained by simply just replacing Z by minus Z, or vice versa. High pass to low pass you can obtain by simply replacing Z by minus Z. But band pass filter to band stop filter you cannot replace by minus Z. This is not possible. But here this is possible. One can go from low pass filter to high pass filter or high pass filter to low pass filter. It is possible. But in the case of band pass to band stop or band stop to band pass, no. Okay, so in a low pass filter, if you replace Z by minus Z, you get a high pass, and vice versa. But if you take a high pass and replace Z by minus Z, and you will get a low pass, right? That is okay. But this is not true about the band pass filter and band stop filter. Therefore, the band stop filter has to be derived ab initio. Okay, so band stop filter has to be derived ab initio. So the simplest second band stop filter that has been worked out by the same trial and error method is h of z is equal to, the denominator it is the same, 1 minus beta times 1 plus alpha z inverse plus alpha times z to the minus 2. In the numerator it's a band stop filter, right? So 1 plus, I need some term, plus z to the minus 2. Let us figure out what this term is. Okay, now the numerator is not 1 plus z to the minus 2 because that fixes the notch frequency at omega equal to pi by 2. So if you take 1 plus z to the minus 2, I have fixed the notch frequency at pi by 2. So if I take 1 plus z to the minus 2, then the notch frequency is fixed. So I introduce another term. The term is minus 2 beta times z inverse. Therefore, my h of z is equal to the denominator 1 minus beta 1 plus alpha times z inverse plus alpha z to the minus 2. In the numerator 1 minus beta 1 minus 2 beta z inverse plus z to the minus 2. So this is the transfer function of band stop filter, and the multiplying constant is now 1 plus alpha by 2. Okay, so now this is the transfer function of band stop filter, and this is not simply changing z to z inverse in the band pass function. It has to be worked out independently and has to be derived ab initio. Now if you put a z is equal to e to the j omega, okay, and then you can find out the magnitude and equate this magnitude to 1 over root 2, then you get the frequency. That frequency is called a notch frequency. Okay, substitute z is equal to e to the j omega, then you will get frequency response function. Take the magnitude and equate the magnitude to 1 by root 2 and then solve this, then you will get a value for the frequency. That frequency is denoted by omega naught, the notch frequency. I'm very sorry, because notch frequency is a frequency at which we need zero attenuation, therefore you make it 0 and then solve it, you will get a notch frequency. Okay, find the magnitude and equate this magnitude to 0, then you get the notch frequency, and that notch frequency is denoted by omega naught. So the characteristics would be like this. This is pi, and this is omega naught notch frequency, and this is 0. Here omega is equal to 0, here omega is equal to omega naught notch frequency. In this point, omega is equal to pi. And this is the frequency axis. This is magnitude of the frequency response function. Okay, so you get a characteristic like this. Okay, this is my magnitude characteristic, where the DC response as well as the response at pi both are equal to how much? 1. It is 1, and this also 1. That is why this normalizing factor comes. Okay, that scaling constant was introduced. If you don't introduce this scaling constant, then this maximum value would have been something else. And now again you can show that this cos of omega naught is equal to beta. The notch frequency can be obtained. How will you show this? You take the magnitude equal to 0, solve this, and then omega naught is equal to cosine inverse of beta. And now what about the bandwidth? Again 3 dB down from the maximum value. Okay, so you take this is a 3 dB down from the maximum value, and this point, let me call this is omega 1, and this point is omega 2. So therefore bandwidth is equal to omega 2 minus omega 1. Again, how will you find out this expression, the expression for the bandwidth? You take h of z, replace z by e to the j omega, and then you will get h of e to the j omega. Take the magnitude and equate this to 1 over root 2 and solve this, and then you can show that cos of bandwidth is equal to what? 2 alpha, the same expression, divided by 1 plus alpha square, or bandwidth is equal to cosine inverse of 2 alpha divided by 1 plus alpha square. What is the bandwidth? Bandwidth is omega 2 minus omega 1. Okay, so once again we have given the same relationship that we had in the band pass filter. Now what is h of z in this case? H of z is 1 minus 2 beta z inverse plus z to the minus 2 divided by 1 minus beta times 1 plus alpha z to the minus 1 plus alpha times z to the minus 2. So in this transfer function, if you take alpha is equal to 1, then you will get, what will you get? The numerator 2 beta z to the minus 1 plus z to the minus 2. The denominator, what is going to happen if you let alpha is equal to 1? You will get 1 minus, this alpha is 1 here, 1 plus 1 2, therefore 2 times beta times z inverse. Then this alpha is 1, so z to the minus 2. So numerator and the denominator here 1 plus, multiplying constant is 1 plus alpha by 2, right? So this alpha is 1, 1 plus 1 2, 2 by 2 1, so this factor will disappear. The numerator and the denominator will get cancelled, so you will get 1. So h of z becomes 1. So in the band stop filter, if you allow alpha is equal to 1, then the transfer becomes 1. What is this 1 represents? This 1 represents an all pass filter. It's a straight line, straight connection, okay? There is no attenuation, no restriction, nothing. And even though you get all pass filter, this filter is useless. It is a trivial. When you get the transfer function h of z equal to 1, this is of course all pass filter APF, but this is a trivial all pass filter. Okay, and it is a useless all pass filter. Okay, a straight connection is also an all pass filter. Agreed? So if alpha is equal to 1, then my h of z simply becomes a constant. So it is a trivial all pass filter in which the magnitude is 1. The angle is identically equal to 0. So we will not make alpha equal to 1. Okay, and in this case alpha has to be less than 1 in order that the poles are inside the unit circle. Okay, now let us take an example. So let me give the value and you can work on it. So let the notch frequency is equal to, let me denote omega naught, that notch frequency is equal to pi by 2, and bandwidth of my band stop filter is pi by 4 as in the band pass filter case. Then you can design the band stop filter. Now let me write down the final answer. This is going to be 1 plus z to the minus 2 divided by 1 plus root 2 minus 1 times z to the minus 2 times 1 by root 2. You can work on this. You know the formula for omega naught, you know the formula for bandwidth, and then you can substitute in the transfer function, then you will get it. So this is the very simple band stop filter. Okay. And then suppose you have a band pass filter like this, and this point is 0 and this point is pi. This is omega axis and this is some note I want to mention here. Suppose this is my band pass filter. Okay, now in this band pass filter omega naught, and the maximum occurs at this point 1, and now the Q is not satisfactory. You want a higher Q. That means you have to narrow down the bandwidth. What is a Q? Q is omega naught by bandwidth. Okay, now if I want to increase the Q value, what can I do? Either I can increase omega naught or decrease the bandwidth. Decrease the bandwidth means what? You are moving towards narrow band. Okay, so therefore when you want to high Q, that means you want to get that means you have to reduce the bandwidth, that is narrow bandwidth. Okay, so that means you have to narrow down the bandwidth. Isn't that right? So what you can do is, the simple thing that you can do is cascade another filter. Okay, so this is h1 of e to the j omega. Take one more filter. See, this value is 1 and this value is, let's say, 0.9, and this value is 0.9, this value is 0.8. Let us assume, okay, this value is 0.8, this is 0.7, and this is 0.7, like this. Same kind of identical filter, take one more filter, let's say h1 of e to the j omega. Now cascade these two guys. If we cascade, then what is going to happen? The response will be squared. So this will be squared with the same type of filter. I will get one more filter like this. I am sorry, I couldn't draw in the same shape. Same shape, same center frequency omega naught. This is 1. this is 0.9 and this is 0.9, 0.8, 0.8, 0.7, like this, and so on and so forth. Now multiply term by term. So what is going to happen? If you multiply, these two are in cascade. So if you multiply this point and this point, again you'll get the same 0.1. Now 0.9 and 0.9, if you multiply, what is going to happen? You'll get 0.08, 0.81. So it comes like this. Instead of 0.9, it becomes 0.8. 0.8 and 0.8, if you multiply, 0.64. And this side also 0.64, 0.8, 0.81. And then 0.7 and here 0.7, if you multiply, 0.49. So therefore your response will go like this, very, very narrow. Initially my bandwidth was, my original bandwidth was like this. My original bandwidth is this one, omega 1, omega 2. Now my bandwidth is this one. Now this bandwidth is, let's say bandwidth 2, and here this bandwidth is 1. Now bandwidth 2 is less than bandwidth 1. So that means essentially I am getting the narrow band pass filter. So how can I achieve this narrow band pass filter? By cascading two band pass filters, so that the bandwidth is reduced and the Q value also increased. But what about this point? This point is 0 and this point is 0. No change in this point. In fact, it goes like this. It goes like this. And it comes like this. And this is pi. So the value at omega is equal to 0 and omega equal to pi doesn't change. It remains as the same. Okay. At omega is equal to 0, then 0 square equal to 0. At omega equal to pi, then again 0 square is equal to 0. So this point, this point, this point and this point will not change, remain same. But all others come down if you cascade a number of such filters. You can get a characteristic like this. So if you cascade two band stop filters, what you would get? This is for band pass filter. Now the next question is, if you cascade two band stop filter, what is going to happen? What would you get? So would you get a better characteristic? No, you get a worse characteristic only for your band pass filter. Okay, you must understand this. Okay, similarly for a low pass filter, you can cascade more low pass filters to get a better characteristic. Cascade two or more low pass filter, you will get a better characteristic. It is not characteristic. Similarly, cascade two or more band pass filter, better characteristic. Similarly, cascade two or more number of high pass filter, again you will get better characteristic. But if you cascade two or more band stop filter, then you will get worse characteristic. That one should remember. Okay, and people particularly in fields like biomedical signal processing, they depend on such intuitions. Okay, so they are people who will give you a filter. You will design a filter, and these are the basic block they will use. Okay, generally they will use 1/2 1 plus Z inverse for low pass filter, 1/2 1 minus Z inverse for the high pass filter, right? And then IIR filter, band stop, band pass filter, and IIR. These are the four filters that they use. Okay, the four filters that you have seen in the IIR case, and we have seen four filters in the IIR case. And if one filter doesn't work, you cascade one more filter. Okay, if one is not sufficient, they will use two of them in cascade. But do not make mistake in the cascade of band stop filter. Okay, never ever cascade band stop filter, only cascade band pass filter, low pass filter, high pass filter. Okay, then you adjust your parameter alpha to be able to get the required bandwidth. Okay, so that's it about band pass filters and band stop filter. In the next lecture we will continue our discussion with all pass filter. Okay, so let me stop at this point. Thank you very much.